Hello there, and welcome to Quiet Science Channel. Tonight, we're embarking on a fascinating journey through time, exploring a possible future where humanity has spread across our solar system. This is a speculative exploration based on current scientific understanding, existing technologies, and the ambitious plans of space agencies and private companies around the world. What you're about to hear is not science fiction, but rather science projection. Every technology, every challenge, and every solution we'll discuss is rooted in real scientific principles and engineering concepts being developed today. While the timeline and specific details remain uncertain, the fundamental possibility of what we'll describe is grounded in physics, chemistry, and the remarkable ingenuity of human problem solving. So settle in as we explore the worlds that might one day become humanity's new homes, the technologies that could make interplanetary civilization possible, and the extraordinary challenges our descendants may face as they venture beyond Earth. And if you enjoy this journey through humanity's potential future among the stars, please consider liking and subscribing to Quiet Science Channel. It helps others discover these explorations of science and possibility. Let's begin our voyage through tomorrow. The Gateway, our return to the Moon. The expansion of humanity across the solar system would necessarily begin not with a single giant leap, but with many careful steps, each one building on the last. And based on current plans, those steps will begin on the surface of the Moon, our oldest companion in the night sky, orbiting just 3 days away from Earth. The Moon represents where humanity would learn to live beyond Earth, where we would practice the skills needed to reach Mars and beyond, where we would establish the infrastructure, supply chains, and technologies that make everything else possible. In the mid-2020s, NASA's Artemis program is actively working to return humans to the lunar surface for the first time in over half a century. Artemis 3 is planned to land near the lunar South Pole, in a region where sunlight touches crater rims for most of the year, and where frozen water hides in permanently shadowed regions nearby. The astronauts would spend nearly a week exploring, collecting samples, and testing equipment designed for long-duration missions. The landing site near the rim of Shackleton Crater has been chosen with great care. This ancient impact structure, nearly 21 kilometers in diameter, sits almost perfectly on the Moon's south pole. Its rim catches sunlight for approximately 75% of the lunar day, an invaluable resource in a world of 2 week-long nights. The permanently shadowed interior harbors water ice mixed with the regolith, undisturbed for perhaps billions of years. The astronauts who would land here would not be merely visitors. They would be pioneers, advanced scouts for the civilization that could follow. They would test new spacesuits designed to allow work for 8 hours at a time, far longer than the Apollo suits permitted. They would deploy scientific instruments to study moonquakes, measure the solar wind, and analyze the composition of the ancient lunar soil. But this would be only the beginning. What could follow is not just flags and footprints, but foundations and infrastructure. Based on NASA's current roadmaps, within a decade of the first Artemis landings, Artemis Base Camp could take shape near Shackleton Crater. The base would consist of modular habitats delivered from Earth and assembled by robots and astronauts working together. Each habitat would be a marvel of engineering, designed to withstand temperature swings of more than 250 degrees Celsius between lunar day and night, to resist micrometeorite impacts, and to provide comfortable living space for crews who may spend months there. The first habitats would arrive deflated, compressed into cargo bays for launch. Once on the surface, they would inflate like balloons, their multi-layered walls stiffening into rigid structures. But these inflatable modules alone would not protect against radiation. Each habitat would be equipped with radiation shielding made from lunar regolith, the dusty soil that covers the moon's surface. The regolith would be piled meters thick over the structures by autonomous bulldozers and excavators, providing protection from cosmic rays and solar radiation that would otherwise make long stays impossible. The process of covering habitats with regolith would be slow and methodical. Robots equipped with scoops and conveyors would gather material from nearby, carefully spreading it in even layers. The regolith is not simply dirt. It's a complex mixture of pulverized rock, minerals, and tiny glass beads created by countless micrometeorite impacts over billions of years. When properly compacted, it forms an excellent radiation barrier, potentially reducing exposure levels to nearly what astronauts experience on the International Space Station. The base would be designed to support crews of 4 to 6 astronauts initially, but with capacity to expand to 20 or more as additional modules arrive. There would be sleeping quarters, each astronaut given a small private cabin barely 2 meters on each side, but luxurious compared to the cramped quarters on spacecraft. Laboratory spaces would be equipped with advanced analytical instruments, allowing geologists to study lunar samples in detail, physicists to conduct experiments in the moon's 1/6 gravity, and biologists to grow plants in carefully controlled conditions. Medical facilities would include diagnostic equipment, a small surgical suite for emergencies, and exercise equipment to help astronauts maintain muscle and bone density in low gravity. The workshops would contain tools for repairing spacesuits, maintaining rovers, and fabricating replacement parts using 3-dimensional printers. Large solar panels would unfold near the crater rim, where sunlight is abundant. These panels would not be the simple flat rectangles used on the International Space Station. They would be sophisticated tracking systems mounted on towers several meters high, designed to follow the sun as it crawls along the horizon during the lunar day. Each panel could generate several kilowatts of electricity, and dozens of them working together would provide enough power for the entire base. But the lunar night presents challenges. Without sunlight for 2 weeks at a time, solar panels would be useless. This is where nuclear reactors would prove essential. Small fission reactors, each about the size of a shipping container, would be deployed a safe distance from the habitats. These kilo-power reactors, currently being developed by NASA and the Department of Energy, are designed to operate for 10 years or more without refueling, generating tens of kilowatts continuously day and night. The base would also include massive battery banks, lithium-ion cells stored in insulated containers. During lunar day, excess solar power would charge these batteries. During lunar night, they would supplement the nuclear reactors, ensuring continuous power supply. The energy management system would be fully automated, constantly balancing generation and consumption, prioritizing life support systems, and alerting crew members if power reserves drop below safe levels. Water would be the key to everything. The discovery of water ice in permanently shadowed craters was one of the most important findings in lunar science. Without this water, establishing a permanent base would be far more difficult and expensive. Mining equipment would excavate regolith from the permanently shadowed craters where temperatures drop to -200 degrees Celsius, and water ice has remained frozen for billions of years. The mining operations would be conducted primarily by robots. The extreme cold and complete darkness of the permanently shadowed regions make human work there difficult and dangerous. Instead, autonomous rovers equipped with scoops and drills would venture into these frozen areas, excavating regolith and loading it into insulated containers. The ice-rich regolith would be transported to processing facilities near the habitats. There, it would be heated in solar ovens, essentially large parabolic mirrors that focus concentrated sunlight onto processing chambers. The heat would cause the ice to sublime, turning directly from solid to vapor without melting. The water vapor would be collected, condensed, and purified through multiple filtration stages to remove any contaminants. The resulting water would be extraordinarily valuable. Astronauts would drink it, of course. They would use it for cooking, for washing, for every aspect of daily life. But water would serve purposes beyond sustaining human life. Electrolysis systems would split water molecules into hydrogen and oxygen gases. The oxygen would be compressed and stored for breathing. The hydrogen would be combined with more oxygen in fuel cells to generate electricity when needed. Or both gases would be stored as rocket propellant for spacecraft launching from the moon. This is called in situ resource utilization, and it would change everything. Instead of carrying all their water and fuel from Earth at costs exceeding $10,000 per kilogram, lunar colonists would make what they need from local materials. This would make missions cheaper, longer, and more sustainable. It would transform the moon from a destination requiring constant resupply to a place that could support itself and even export resources. But the moon offers more than just water. Its regolith contains silicon, aluminum, iron, titanium, and other metals that could be extracted and processed. The extraction methods would vary depending on the element. Silicon could be refined through carbothermic reduction, heating regolith with carbon to temperatures above 1600 degrees Celsius. Aluminum extraction would be more complex, requiring electrolysis of molten minerals. Iron could be separated magnetically, since much of it exists as metallic particles from ancient asteroid impacts. Three-dimensional printers could use the regolith mixed with binding agents to construct new buildings, landing pads, and roads connecting different parts of the base. These printers would not be the small desktop devices found in homes and offices on Earth. They would be massive machines mounted on tracked vehicles, capable of extruding material at rates of tons per hour. The structures they create would be built layer by layer, shaped by robotic arms that work tirelessly in the airless environment. A landing pad might take several weeks to construct, with the printer slowly tracing back and forth, depositing material in precise patterns. The regolith would be mixed with a binder, sometimes simply molten sulfur extracted from volcanic minerals, sometimes more complex polymers brought from Earth. The mixture would be extruded through nozzles, hardening rapidly in the lunar vacuum. The printers would create walls thick enough to protect against micrometeorites, the tiny space rocks that constantly pepper the moon's surface at velocities of several kilometers per second. These impacts, while individually tiny, can damage equipment and even puncture spacesuits. Buildings constructed with thick regolith walls would be essentially immune to this hazard. They would build radiation shelters where astronauts could retreat during solar storms. When the sun erupts with a coronal mass ejection, high-energy particles flood through space. On Earth, our magnetic field deflects most of this radiation. On the moon, there is no such protection. Astronauts would need to take shelter in specially designed chambers with extra thick walls, sometimes spending hours or even days inside while the storm passes. They would even construct greenhouses with transparent domes, where crops would grow in hydroponic systems under artificial lights supplemented by focused sunlight. These greenhouses would be engineering marvels. The transparent sections would be made of specialized glass or plastic that filters out harmful ultraviolet radiation while allowing visible light through. The structures would need to maintain pressure, temperature, and humidity while sitting exposed on the lunar surface. Inside, rows of plants would grow in nutrient solution, their roots suspended in water rather than soil. Lettuce, herbs, strawberries, tomatoes, and other quick-growing crops would provide fresh food to supplement packaged meals brought from Earth. The psychological benefits of fresh vegetables and the ability to tend growing plants would prove as valuable as the nutrition they provide. The greenhouses would also serve another crucial function. They would help recycle carbon dioxide and generate oxygen. Plants breathe in carbon dioxide exhaled by astronauts and machinery, using it to build their tissues while releasing oxygen as a byproduct. The more plants growing, the less the base's life support systems would need to work to scrub carbon dioxide from the air and generate oxygen from water electrolysis. Transportation would evolve as the base expands. The first rovers would be simple, unpressurized vehicles, essentially lunar dune buggies with oversized wheels and electric motors. Astronauts would need to wear full spacesuits to ride them, exposed to vacuum and temperature extremes. But these rovers would allow exploration far beyond walking distance. As the base grows, pressurized rovers would arrive. These would be essentially small mobile habitats equipped with life support, sleeping quarters, and scientific instruments. A pressurized rover might be 5 meters long and 3 meters wide, with space for 2 or 3 astronauts to live for weeks at a time. They would have airlocks for entering and exiting, communication systems for staying in contact with the base, and extensive battery banks, or even small nuclear reactors for power. Crews could spend weeks away from the main base in these rovers, venturing hundreds of kilometers across the surface, exploring new regions and prospecting for resources. They would drive down into ancient lava tubes, massive tunnel systems carved by flowing lava billions of years ago. These tubes can be several kilometers long and hundreds of meters in diameter, natural caverns that might serve as ideal locations for future underground cities, protected from radiation and micrometeorites by thick rock ceilings. The astronauts might discover that some lava tubes show signs of past volcanic activity more recent than expected. Pockets of trapped gases could indicate the moon may not be as geologically dead as once thought. These discoveries would have implications for understanding the moon's interior structure and thermal evolution. Above the surface, spacecraft would come and go with increasing frequency. Commercial companies are already developing lunar cargo services, planning to deliver supplies, equipment, and new modules to expand future bases. Companies like SpaceX, Blue Origin, and newer firms founded specifically for lunar operations are competing for contracts. They envision landing cargo ships on prepared pads, with autonomous vehicles offloading equipment and supplies before the ships return to Earth for refurbishment and reuse. NASA and international partners are working alongside private enterprises from companies based in the United States, China, Japan, Europe, and India. The moon could become the first truly international outpost, a proving ground for the cooperation that would be necessary for more distant destinations. Astronauts from different nations would work side by side, sharing resources, expertise, and responsibilities. Cultural differences might sometimes create minor friction. Schedules would need to accommodate different time zones for communicating with mission control centers around Earth. Meals would reflect diverse cuisines, with freeze-dried curry alongside freeze-dried pasta. But overall, international crews would likely bond through shared challenges and the profound experience of living and working on another world. By the 2030s, according to various space agencies' projections, multiple bases could dot the lunar landscape. Some would focus on scientific research, studying the moon's geology, and searching for clues about the early solar system. The rocks brought back by Apollo missions revealed that the moon formed from debris ejected when a Mars-sized object collided with early Earth, but many questions remain about the details of lunar evolution. Research stations could be established at sites of particular scientific interest. One base might sit in the center of the vast South Pole Aitken Basin, a giant impact crater over 2,000 kilometers in diameter and 13 kilometers deep. This ancient impact excavated material from deep in the moon's interior, possibly even exposing parts of the mantle. Studying these rocks would provide insights into the moon's composition and formation that cannot be obtained anywhere else. Another base might operate near the young crater Aristarchus, which shows evidence of relatively recent volcanic activity in geological terms. The dark material within this crater may be only a few 100 million years old rather than billions, indicating volcanic eruptions long after scientists believed such activity had ceased. Understanding when and why volcanism occurred helps piece together the moon's thermal history. Other bases would be industrial facilities, mining operations that extract metals and manufacture components for spacecraft and habitats. These operations would grow increasingly sophisticated as equipment and expertise accumulate. What begins as simple excavation could evolve into complex metallurgical processing. Refineries would extract pure metals from regolith using a variety of methods. Solar furnaces, parabolic mirrors, focusing sunlight to temperatures exceeding 2,000 degrees Celsius, would melt minerals and allow metals to be separated. Electrolysis would break down compounds that resist thermal processing. Chemical methods would dissolve and precipitate specific elements. The extracted metals would be formed into structural components, beams and panels and fittings that could be assembled into frameworks for habitats, greenhouses, and spacecraft. Manufacturing facilities would use three-dimensional metal printers to create complex parts with precision impossible in Earth's gravity. Some components would be better made in the moon's vacuum environment, allowing techniques like electron beam welding that would be difficult or impossible on Earth. Still, other bases would serve as spaceports, waypoints for missions heading deeper into the solar system. These facilities would include large propellant tanks storing liquid oxygen and liquid hydrogen manufactured from lunar water. Maintenance hangars would provide protected spaces where spacecraft could undergo repairs and upgrades. Hotels might offer accommodations for crews transferring between vehicles or waiting for launch windows to open. The spaceport facilities could be bustling with activity. Cargo ships would arrive from Earth and eventually Mars. Mining vessels would depart for the asteroid belt. Passenger ships would board travelers heading to orbital stations or other destinations. Fuel tankers would load propellant for delivery to depots throughout cislunar space. The loading docks and landing pads would operate continuously, a constant flow of arriving and departing craft. Lunar orbit would host the Gateway, a small space station that NASA is currently developing to serve as a staging point for surface missions and a rest stop for crews traveling between Earth and the Moon. The Gateway would consist of several modules including habitation quarters, laboratories, a small medical bay, and large docking ports where multiple vehicles could connect simultaneously. The Gateway would be where spacecraft refuel using propellant manufactured on the lunar surface. Tankers would launch from the Moon's relatively shallow gravity well, delivering liquid oxygen and liquid hydrogen to the station's storage tanks. This would make it possible for spacecraft arriving from Earth to top off their tanks before heading to Mars or the asteroid belt, without needing to carry all their propellant from Earth's surface. It would be where astronauts transfer between vehicles, moving from the spacecraft that brought them from Earth to the landers that would carry them to the moon's surface. Where supplies are sorted and redistributed, cargo containers shifted from one ship to another, depending on ultimate destination, where damaged equipment is brought for repair before being returned to service. The gateway would become the hub of a growing transportation network. Flight controllers would coordinate the complex dance of arriving and departing vessels. Traffic around the moon would increase year by year, with dozens of spacecraft potentially operating in lunar orbit simultaneously. Navigation systems would track their positions constantly, ensuring safe separation and coordinating rendezvous maneuvers. The moon would teach humanity how to live and work in an environment fundamentally hostile to life, how to recycle every drop of water, every breath of air. Systems would become progressively more efficient, minimizing losses and waste. Water recycling could achieve 99% efficiency through multiple purification stages. Air scrubbers would remove carbon dioxide and trace contaminants, while oxygen generators split water to replenish what is lost. How to maintain equipment in vacuum and extreme temperature swings. Tools and materials behave differently in airless conditions. Lubricants evaporate instantly in vacuum, requiring special formulations. Metals expand and contract dramatically as temperatures swing from plus 120 degrees in sunlight to minus 150 in shadow. Engineers would learn through experience what works and what fails, how to grow food where nothing has ever grown before. Greenhouses would expand from experimental plots to substantial agricultural facilities, producing tons of fresh vegetables. Experiments with different crops would identify which species thrive in lunar gravity and artificial conditions. Some plants would adapt readily, others would struggle. Researchers would develop new varieties optimized for space agriculture. How to build shelter from local materials. The transition from habitats brought from Earth to structures manufactured entirely from lunar resources would represent a major milestone. When crews begin living in buildings made entirely from regolith and metals extracted from lunar soil, the moon would take a huge step toward true self-sufficiency. How to cooperate across national boundaries for a common goal. The international nature of lunar development could set precedents for later expansion throughout the solar system. Treaties would establish frameworks for sharing resources, resolving disputes, and ensuring that the benefits of space development flow back to Earth. These lessons would prove invaluable when humanity reaches for Mars. The Red Horizon, colonizing Mars. Mars has always occupied a special place in human imagination. The Red Planet, named after the god of war, but promising a future of peace and exploration. The world most like Earth in the solar system, yet profoundly alien. The destination that represents humanity's next giant leap. By the late 2020s, according to current plans from SpaceX and other organizations, that leap could be underway. SpaceX is leading the charge with Starship, a fully reusable spacecraft designed specifically for Mars missions. Standing over 120 meters tall when stacked atop its super heavy booster, Starship is designed to be the most powerful rocket ever built. Its stainless steel hull gleams in the Florida sun as it undergoes testing for eventual cargo missions to Mars. According to SpaceX's publicly stated timeline from 2025, the company aims to launch uncrewed starships to Mars during favorable launch windows, each carrying equipment and supplies for the first human crews. These cargo ships would carry everything needed to establish a Mars base: habitat modules, solar panels, life support systems, rovers, drilling equipment, and supplies for manufacturing fuel from Martian resources. The spacecraft would travel for approximately 6 months, using the most efficient trajectories between Earth and Mars. They would arrive during the Martian southern spring, when conditions are most favorable. One by one, they would descend through the thin atmosphere, using a combination of aerodynamic braking and powerful Raptor engines to land vertically on the surface. Landing on Mars presents more challenges than landing on the Moon. Mars has an atmosphere, but it's too thin to rely on parachutes alone for large spacecraft. Too thick to ignore with pure propulsion. Starship would need to thread the needle, using its heat shield to slow down during atmospheric entry, then flipping vertical and firing its engines for the final descent. If these initial cargo missions succeed, human crews could follow in subsequent launch windows. According to SpaceX's aspirational timeline, astronauts might board starships for the journey within the next decade or two. They would travel in relative comfort with private sleeping quarters, exercise equipment to combat muscle loss in zero gravity, laboratories where they could conduct experiments during the long voyage, and common areas where they eat meals and spend their off hours. The ships might spin slowly to provide a small amount of artificial gravity, enough to reduce the health problems associated with prolonged weightlessness. Large windows would offer views of Earth shrinking behind them and Mars growing larger ahead, a rust-colored sphere calling them forward. When they arrive, they would find the cargo starships already waiting, standing like steel towers on the Martian plain. Robots would have already begun unpacking equipment and preparing the site. Solar panels would spread across the surface. A nuclear reactor would provide backup power. Initial tests of the propellant production system would show promise. The astronauts would land nearby and begin the work of establishing humanity's first permanent settlement on another planet. A Mars base could grow in the southern highlands, near the equator, where temperatures are relatively mild and solar power is abundant year-round. The base would consist of interconnected habitats partially buried under Martian regolith for radiation protection. Each habitat would be a cylindrical module with living quarters, laboratories, greenhouses, workshops, and storage areas. The greenhouses would be crucial. Plants would not only provide food, but also help recycle air and water. Under LED lights, tuned to optimal wavelengths, crops would grow in hydroponic systems using water extracted from underground ice deposits. Potatoes, lettuce, tomatoes, herbs, and other fast-growing vegetables would supplement the packaged food brought from Earth. Eventually, the colonists would aim for complete self-sufficiency in food production. Water would come from subsurface ice deposits detected by orbital radar. Drilling robots would bore deep into the regolith, heating the ice and collecting the resulting water vapor. This water would be filtered, purified, and stored in large tanks. Every drop would be precious and carefully recycled through systems that recover water from breathing, sweating, and waste. The atmosphere on Mars is 95% carbon dioxide, with tiny amounts of nitrogen and argon. The atmospheric pressure is less than 1% of Earth's, far too low for humans to survive without pressure suits. But that carbon dioxide would become a resource. Chemical processors would split it into oxygen for breathing and carbon for manufacturing. Combined with hydrogen from water, it would produce methane for rocket fuel. This fuel production would be essential for the return trip to Earth. Starships would arrive on Mars with enough propellant for landing, but would need to refuel for the journey home. The in-situ propellant production facility would become operational within months of the first human arrival, manufacturing thousands of tons of liquid methane and liquid oxygen. As the base grows, specialized facilities would be added. A workshop with three-dimensional printers would manufacture spare parts and new tools from Martian materials. A small medical center would handle injuries and illnesses. A communications array would maintain constant contact with Earth. Those signals would take between 4 and 24 minutes to cross the distance depending on the planet's orbital positions. Transportation on Mars would begin with simple pressurized rovers, essentially small vehicles with inflatable airlocks. Colonists would wear spacesuits whenever they venture outside the habitats. The suits would be more advanced than those used on the Moon, designed for long-duration use with better mobility, improved heating systems, and heads-up displays that project information directly onto the helmet's faceplate. Later, larger pressurized rovers would serve as mobile habitats, allowing crews to embark on expeditions lasting weeks. These vehicles would traverse the Martian landscape, exploring canyons, climbing crater rims, investigating the channels carved by ancient rivers. They would search for signs of past or present life, study the planet's geology, and prospect for mineral deposits. The colonists would discover that Mars is a world of stunning beauty. Rust-colored plains stretch to horizons 3 times farther away than on Earth due to Mars's smaller size. Ancient volcanoes rise to heights that dwarf anything on Earth. Olympus Mons stands 21 kilometers tall, 3 times the height of Mount Everest. Valles Marineris, a canyon system that would stretch across the United States from coast to coast, cuts deep into the surface. The sky is different colors there. During the day, it's a butterscotch hue due to fine dust suspended in the thin atmosphere. Sunsets are blue, the opposite of Earth, as dust scatters red light and allows blue wavelengths through. At night, 2 small moons race across the sky. Phobos orbits so fast it rises in the west and sets in the east, crossing the sky in just a few hours. Deimos moves more slowly, a tiny point of light. By the late 2030s or 2040s, according to various projections, a Mars base could be thriving. Dozens of people might live and work on the surface. New starships would arrive every 26 months during optimal launch windows, bringing more colonists, equipment, and supplies. Some crew members would rotate back to Earth after 2-year tours, but others might choose to stay permanently, becoming true Martians. Additional bases could be established in other locations. A base might grow near the polar ice caps, where massive deposits of water ice lie just beneath the surface. Mining operations would extract this ice in enormous quantities, not just for local use, but potentially for export to facilities throughout the inner solar system. A third base might be built inside a lava tube near Arsia Mons, one of the massive shield volcanoes. The lava tube would provide natural protection from radiation and micrometeorites. Its interior could be sealed and pressurized, creating a huge enclosed space where colonists could move around without spacesuits. Trees might be planted, creating an underground forest. A small lake could fill one section, fed by melted ice. A Martian economy could develop around several key industries. Mining operations would extract iron, aluminum, and rare earth elements from the regolith. These metals might be shipped to orbital facilities for processing and manufacturing. Water could become an export commodity, launched into space and sold to other colonies and space stations throughout the solar system. The thin atmosphere, while challenging for humans, could prove ideal for certain types of manufacturing. Vacuum or low-pressure processes that require expensive chambers on Earth could be conducted in the open on Mars. Pharmaceutical companies might establish facilities to manufacture drugs and materials impossible to produce in Earth's denser atmosphere. Scientific research would flourish. Mars would serve as an ideal platform for astronomy, with clear skies and no light pollution. Radio telescopes in the polar regions would listen for signals from distant stars. Particle accelerators could take advantage of the straight, flat terrain to reach unprecedented lengths. but the ultimate vision reaches far beyond a few bases. Some scientists and engineers dream of transforming Mars itself, slowly increasing the atmospheric pressure and temperature until humans could walk on the surface with just a simple breathing mask rather than a full pressure suit. This process, called terraforming, would take centuries or even millennia and remains highly speculative. The first steps have been theorized. Factories could produce greenhouse gases that might slowly warm the planet. Mirrors in orbit could focus additional sunlight onto the polar ice caps, accelerating their sublimation. Deep drilling might tap underground reservoirs of frozen carbon dioxide, releasing it into the atmosphere. Whether these efforts could succeed remains uncertain and is purely speculative at this point. But on Mars, humanity would prove it can not only survive on another world, but potentially thrive, building a civilization that could endure long after those who established it have passed into history. The asteroid frontier, mining the belt. Between Mars and Jupiter lies a realm of ancient fragments, countless rocks tumbling through space, remnants from the solar system's formation 4.5 billion years ago. The asteroid belt contains hundreds of thousands of objects, from dust-sized particles to the dwarf planet Ceres, nearly 1,000 kilometers in diameter. This scattered debris field represents a potential economic frontier, a realm where fortunes might be made by those brave enough to venture into the dark spaces between the worlds. Asteroid mining would likely begin not with human prospectors, but with robots. Small spacecraft would launch from Earth and Mars, traveling along carefully calculated trajectories to rendezvous with specific asteroids identified by telescopes as particularly valuable. These targets fall into several categories: carbonaceous asteroids, dark and rich in water ice, organic compounds, and volatiles like nitrogen and carbon dioxide. These resources are crucial for sustaining human life in space. Water becomes drinking water, oxygen for breathing, hydrogen for fuel. The organic compounds can be processed into materials for manufacturing or even food for colonists. Metallic asteroids, composed primarily of iron and nickel, often with significant quantities of platinum group metals like platinum, palladium, and rhodium. These metals are rare on Earth but abundant in certain asteroids, concentrated during the early solar system's formation. A single metallic asteroid, a few hundred meters across, could contain more platinum than has ever been mined on Earth. Stony asteroids, made of silicate rock, contain valuable minerals and can be processed for construction materials. The first commercial asteroid mining missions are already being planned in the mid-2020s. Companies like Astroforge are developing technologies to send small spacecraft to rendezvous with near-Earth asteroids, relatively small rocks that pass close to Earth's orbit. In February 2025, Astroforge's Odin spacecraft launched toward asteroid 2022 OB5, demonstrating key technologies for future mining operations. These early missions serve as learning experiences. The spacecraft must navigate to the asteroid, match its rotation, and anchor to its surface using harpoons or drills. Once secured, mining equipment would begin extracting material. For carbonaceous asteroids, the process would be relatively simple. Scoop up regolith, heat it in a solar oven, and collect the water vapor that boils off. The water would then be frozen and stored for transport. For metallic asteroids, the process would be more complex. Mining robots would extract chunks of ore and process them using solar furnaces that focus concentrated sunlight to melt the metal. The molten metal would be cast into ingots or shaped into structural components. The refined metal would then be loaded into transport containers for shipment to construction facilities in lunar or Martian orbit. Transportation is the key challenge. Asteroids are scattered across vast distances, and moving massive quantities of material requires enormous amounts of energy. Early mining operations would focus on near-Earth asteroids specifically because they're easier to reach. These asteroids have orbits that bring them relatively close to Earth, requiring less fuel for spacecraft to reach them. But the real wealth lies deeper in the belt between Mars and Jupiter, where the largest and most valuable asteroids orbit. Reaching these would require different strategies. One approach would use slow but efficient propulsion. Ion drives, powered by solar panels or nuclear reactors, accelerate charged particles to generate thrust. While the thrust is tiny compared to chemical rockets, ion drives can run for years, gradually building up enormous velocities. Cargo tugs equipped with these drives could slowly push or tow asteroids, shifting their orbits over months or years to bring them closer to Earth or Mars, where they could be processed more easily. Another approach would bring the processing to the asteroids. Mobile refineries, essentially automated factories in space, would travel from asteroid to asteroid, extracting resources and manufacturing products that could be sold elsewhere in the solar system. These factories would operate autonomously for years, only requiring occasional maintenance from visiting repair crews. By the 2040s or 2050s, according to industry projections, the asteroid mining industry could have matured significantly. Dozens of companies might operate hundreds of mining spacecraft. Tens of thousands of robots could work in the belt, extracting resources that fuel a growing solar system economy. The wealth flowing from the asteroids could transform space development. Water from carbonaceous asteroids would make it possible to establish fuel depots throughout the inner solar system. Spacecraft would no longer need to carry all their propellant from Earth. They could refuel at stations in lunar orbit, Mars orbit, or along routes to the outer planets. Platinum group metals from metallic asteroids might flow back to Earth, where they're used in everything from catalytic converters to fuel cells to electronics. The influx of these metals could drop their price significantly, making them accessible for applications previously too expensive. Iron and nickel from metallic asteroids could become the primary construction materials for large structures in space. Orbital factories would receive shipments of refined metal and manufacture everything from spacecraft hulls to habitat modules to structural components for massive rotating space stations. Some asteroids might be captured entirely and brought into orbit around Earth or Mars. These captured asteroids would become permanent resources, small mountains of valuable material that could be mined for decades or centuries. Others might be hollowed out and converted into habitats, with the excavated material used for construction elsewhere. The asteroid belt could also become home to small colonies of miners and their families. These settlements would be located on the largest asteroids or inside hollowed-out smaller ones. Life there would be challenging, with minimal gravity and no natural atmosphere. But the economic opportunities might attract thousands of people willing to endure hardships for the chance to stake claims and build fortunes. One such settlement might grow inside the asteroid Psyche, a massive metallic asteroid 200 kilometers in diameter that may be the exposed iron core of a destroyed protoplanet. The colony would burrow deep into the metal, creating pressurized chambers where thousands of people could live and work. Outside, mining operations would extract iron, nickel, and precious metals worth trillions of dollars. The asteroid Ceres, the largest object in the belt, could become another major settlement. At 946 kilometers in diameter, Ceres is massive enough that its own gravity has pulled it into a spherical shape. Recent discoveries have revealed that Ceres has a subsurface ocean of liquid water beneath an icy crust, making it one of the most promising locations for a permanent colony. Habitats might be constructed on Ceres's surface and in subsurface caverns accessed through mining tunnels. The settlement could eventually grow to house tens of thousands or more, becoming a hub for the asteroid belt. Ceres would serve as a waypoint for transportation and commerce, a meeting point for missions traveling between the inner and outer solar system. The potential success of asteroid mining suggests that space could become economically self-sustaining. The resources extracted from asteroids might exceed the value of investments required to access them. Profits from mining operations could fund new missions, new technologies, new settlements. The solar system might truly begin to open up as humanity's economic reach extends farther and farther from Earth. Venus, the cloud cities. While Mars captures most of the attention as humanity's next home, another world beckons with possibilities both strange and promising. Venus, Earth's sister planet, named after the goddess of love, but possessing a surface that would melt lead and crush spacecraft under pressures 90 times greater than Earth's atmosphere. Yet, paradoxically, Venus may offer some of the most Earth-like conditions in the entire solar system, if one knows where to look. The key is to look up. At an altitude of 50 to 55 kilometers above Venus's hellish surface, conditions are surprisingly pleasant. The temperature ranges from 0 to 50 degrees Celsius, comfortably within the range humans can tolerate. The atmospheric pressure is approximately the same as sea level on Earth. And most remarkably, regular Earth air, a mixture of nitrogen and oxygen, would act as a lifting gas in Venus's dense carbon dioxide atmosphere. This means that a habitat filled with breathable air would naturally float at this altitude, like a balloon filled with helium on Earth. No complex lifting mechanisms needed. The habitat floats simply by existing. This concept, proposed by NASA scientist Jeffrey Landis and others, envisions floating cities in the clouds of Venus, aerostats that would drift in the upper atmosphere where humans could live in relative comfort. The first missions to Venus's atmosphere would be scientific probes, not human habitats. NASA has studied concepts like the HAVOC program, which envisions piloted missions to Venus, where crews would never reach the surface. Instead, they would explore the cloud layer, spending 30 days floating in specially designed aerostats while conducting scientific observations. The aerostats would be large blimp-like structures filled with breathable air. Solar panels on the upper surface would generate electricity. The crew would live in a pressurized gondola suspended beneath the envelope. Life support systems would scrub carbon dioxide from the air and generate oxygen through electrolysis of water brought from Earth. The view would be spectacular, but alien. The crew would float through yellow-orange clouds of sulfuric acid, their habitat protected by acid-resistant coatings of fluoropolymers. Below them would stretch an impenetrable haze that conceals the volcanic surface. Above, the carbon dioxide atmosphere would thin gradually toward space. Winds averaging 300 kilometers per hour would propel the habitat around the planet, circling it in just 4 Earth days. These missions would prove that humans can survive comfortably in Venus's atmosphere. But establishing permanent colonies would require solving several challenges. The first is the sulfuric acid. The clouds of Venus are not water vapor, but droplets of concentrated sulfuric acid. Any structure must be coated with materials that resist corrosion. Fortunately, such materials exist. Teflon and other fluoropolymers are essentially immune to sulfuric acid and can protect the habitat's exterior. The second challenge is water. Venus has almost no water in its atmosphere or on its surface. Every drop would need to be imported or manufactured from hydrogen brought from Earth or extracted from the solar wind. Strict recycling protocols would recover water from every possible source, similar to systems used on space stations. The third challenge is radiation protection. While Venus's thick atmosphere shields the surface from cosmic radiation, the cloud layer offers less protection than Earth's atmosphere. However, the carbon dioxide atmosphere would provide more shielding than the near vacuum of space, making Venus's clouds safer than most locations in the solar system. Despite these challenges, the advantages could be compelling. The similarity to Earth conditions means colonists would need no pressure suits or radiation shielding beyond what the atmosphere naturally provides. They could work outside their habitats wearing simple acid-resistant suits with air supplies, not bulky spacesuits. The moderate temperatures mean heating and cooling requirements would be minimal compared to other worlds. By the 2050s or later, according to some speculative proposals, the first permanent cloud cities might take shape. These would not be small research outposts, but potentially substantial habitats housing hundreds or eventually thousands of people. The habitats would be constructed from lightweight yet strong materials, using tensegrity structures or geodesic domes inspired by Buckminster Fuller. These designs maximize strength while minimizing mass. The habitats would rotate slowly to ensure even exposure to sunlight and prevent overheating on one side. Inside, life would resemble a mixture of life on Earth and life on a ship. Multi-level decks would contain living quarters, laboratories, agricultural facilities, workshops, and recreational spaces. Residents would cultivate gardens in hydroponic bays, where tomatoes, herbs, and flowering plants grow under carefully controlled conditions. The plants would not only provide food and beauty, but also help recycle air and water. The cities would drift with the winds, circling Venus every 4 days. However, they wouldn't be completely at the mercy of atmospheric currents. By adjusting altitude slightly, moving up or down in the atmosphere where different wind speeds prevail, the habitats could change their velocity and gradually modify their paths. Over time, entire fleets of habitats could coordinate their movements to stay grouped together, creating floating metropolitan areas. Transportation between habitats would occur via small airships or aircraft. Venus's dense atmosphere and moderate gravity make powered flight remarkably easy. Human-powered flight would even be possible. A person wearing artificial wings could fly through the Venusian atmosphere using only muscle power, something impossible on any other world. The cloud cities could develop several economic activities. Scientific research would flourish in the unique environment. The upper atmosphere of Venus is an ideal place to study planetary atmospheres, cloud dynamics, and atmospheric chemistry. Solar astronomy benefits from the lack of ground-based light pollution. Mining operations might lower robots on cables to the surface, where they would collect samples of rock and metal for analysis. While the surface conditions make permanent habitation impossible with current technology, remote-controlled operations could extract valuable materials. Venus could also become a waypoint for missions traveling between Earth and the inner solar system. The planet's position and orbital mechanics make it useful for gravity assist maneuvers that can save fuel for spacecraft heading to Mercury or back to Earth. Perhaps most intriguingly, some scientists have proposed that in the very long term, Venus's atmosphere could be gradually transformed through a process similar to terraforming Mars, but in reverse. Instead of warming and thickening an atmosphere, the goal would be to cool Venus and reduce its atmospheric pressure. This remains highly speculative. The cloud cities themselves might play a role in this transformation. Floating solar shades could reflect sunlight, cooling the planet. Atmospheric processors could convert carbon dioxide into stable compounds that settle out of the atmosphere. Over centuries or millennia, Venus might slowly become more Earth-like. Whether such ambitious engineering is practical remains uncertain and purely theoretical. But in the cloud cities of Venus, humanity would prove once again that even the most unlikely worlds could potentially become home with sufficient ingenuity and determination. The Jovian system, moons of giants. Beyond the asteroid belt, the solar system changes character dramatically. The worlds here are no longer small rocky planets, but gas giants, massive spheres of hydrogen and helium with no solid surfaces to stand on. Jupiter, the king of planets, is so large that more than 1,000 Earths could fit inside its volume. But Jupiter itself is not the destination. Its moons are. Jupiter possesses at least 95 confirmed moons, from tiny captured asteroids to 4 massive satellites discovered by Galileo in 1610: Io, Europa, Ganymede, and Callisto. These 4 Galilean moons are worlds in their own right, each larger than Earth's moon, and each offering unique opportunities and challenges for potential colonization. However, Jupiter's intense radiation belts pose a formidable obstacle. The planet's powerful magnetic field traps charged particles, creating radiation zones far more intense than Earth's Van Allen belts. Io, the innermost Galilean moon, receives roughly 36 sieverts of radiation per day, enough to kill an unshielded human in hours. Europa, the second moon, receives about 5 sieverts per day, still lethal without protection. These radiation levels make Io and Europa extremely challenging for human settlement. Only Ganymede and Callisto, orbiting farther from Jupiter, offer radiation environments manageable with reasonable shielding. Callisto, the outermost Galilean moon, would likely become the first target for colonization in the Jupiter system. Orbiting at a distance of 1.88 million kilometers from Jupiter, Callisto sits just beyond the planet's most intense radiation belts, receiving only about 0.01 sieverts per day, within acceptable limits for long-term habitation. Callisto is an ancient geologically dead world, its surface saturated with impact craters dating back billions of years. The moon is composed of roughly equal parts rock and water ice, making it essentially a giant dirty snowball 4,800 kilometers in diameter. The first missions might arrive in the 2050s or later after 9-month journeys from Earth. Nuclear electric propulsion systems, far more efficient than chemical rockets, would make the trip practical. The spacecraft would carry equipment for establishing a research base in a crater near Callisto's equator. The base would be built partially underground, with regolith piled on top for additional radiation shielding. Nuclear reactors would provide power since sunlight is only about 4% as intense at Jupiter's distance as at Earth. The colonists would extract water ice from the surrounding terrain, melting it for drinking water, and splitting it into hydrogen and oxygen for fuel and breathing. Life on Callisto would be austere but manageable. Gravity is about 14% of Earth's, strong enough to make movement feel natural, but weak enough that care must be taken not to jump too high and hit ceilings. The surface is airless and cold, averaging minus 139 degrees Celsius, but the habitats would be warm and comfortable inside. From Callisto, exploration missions would venture to the other moons using small spacecraft. Europa would be the primary target of interest. Europa, slightly smaller than Earth's moon, is covered in smooth water ice that hides one of the most tantalizing secrets in the solar system: a global ocean of liquid water beneath the ice, containing potentially twice as much water as all of Earth's oceans combined. Tidal heating from Jupiter's gravity keeps this ocean liquid despite Europa's frigid surface temperature of -160 degrees Celsius. Cracks and ridges crisscross the ice, evidence of geological activity. In some regions, water or slushy ice may reach close to the surface. The possibility of life in Europa's ocean has captivated scientists since the Voyager probes first imaged the moon in 1979. Could living organisms exist in those dark waters, surviving on chemical energy from Europa's rocky core, the way tube worms near hydrothermal vents do on Earth? Finding out would require drilling through the ice. The ice shell is estimated to be 15 to 25 kilometers thick, too deep for simple drilling operations. Instead, robotic cryobots would melt their way down, using nuclear power to heat their forward end while anchoring equipment to prevent them from floating back up. The descent would take months. Finally, the probe would break through into the ocean below. It would deploy sensors, cameras, and sampling equipment, all connected to the surface by a fiber optic tether. The first images from Europa's ocean could stun the world. If the ocean is not the pitch-black void expected, if bioluminescent organisms drift in the water, glowing softly like deep-sea jellyfish on Earth, if complex organic molecules are detected, if signs of metabolic activity exist, then living ecosystems might exist there, life that evolved completely independently from Earth. Such a discovery would transform humanity's understanding of its place in the cosmos. Life would not be unique to Earth. The universe would likely teem with living things, and Europa's ocean would become the most important scientific site in the solar system. Protecting Europa's potential biosphere would become paramount. Strict protocols would prevent contamination. All equipment sent to the moon would be sterilized more thoroughly than anything sent to Mars. Any bases established would remain on the surface, limited to scientific research. Large-scale colonization of Europa would be postponed until scientists fully understand what lives in its ocean and ensure that human presence won't harm it. Ganymede, Jupiter's largest moon and the largest satellite in the entire solar system, would offer better prospects for colonization. At 5,268 kilometers in diameter, Ganymede is larger than the planet Mercury. It possesses the only natural magnetic field of any moon, providing some protection from Jupiter's radiation at low latitudes. Like Europa and Callisto, Ganymede has a subsurface ocean, but it also has a complex internal structure with multiple layers of ice and water, making it geologically fascinating. The surface is divided between ancient dark terrain, covered in craters, and younger bright terrain with grooves and ridges. Bases on Ganymede might focus on resource extraction and manufacturing. Water ice is abundant and easily accessible. Metals and minerals could be mined from the rocky core. The moon's moderate gravity, about 14% of Earth's, is enough to make construction easier than in microgravity, but low enough to allow efficient launching of materials to Jupiter orbit. The Jovian system could gradually develop into an economic hub for the outer solar system. Materials from the moons would be processed in orbital facilities that circle Jupiter at distances beyond the worst radiation. These facilities would manufacture components for spacecraft, habitats, and infrastructure throughout the outer planets. Jupiter's immense atmosphere could become another resource. While landing on Jupiter is impossible, aerostats might descend into the upper atmosphere to harvest hydrogen and helium-3. Helium-3 is rare on Earth but abundant in Jupiter's atmosphere, and it's a potential fuel for fusion reactors. If controlled fusion power becomes practical, Jupiter could supply fuel for the entire solar system. The view from the Galilean moons would be spectacular. Jupiter would dominate the sky, a vast sphere striped with colorful cloud bands and dotted with storms. the Great Red Spot, a hurricane larger than Earth that has raged for centuries, would be plainly visible. The planet goes through phases as seen from the moons, waxing and waning like Earth's moon does when viewed from Earth. The colonists would watch in awe as the other moons transit across Jupiter's face or cast shadows onto the cloud tops. They would observe lightning storms in Jupiter's atmosphere, flashing like fireflies across the night side. They would study the intricate dance of the Galilean moons, locked in orbital resonance where Io completes 4 orbits, for every 2 of Europa and every 1 of Ganymede. Life in the Jupiter system would be challenging, but potentially rewarding. The radiation would require constant vigilance and sophisticated shielding. The distance from Earth means communication delays of at least 40 minutes round trip, making real-time conversations impossible. Supplies from Earth would take months to arrive, but the colonists would develop self-sufficient communities, relying on locally produced resources and creating their own culture distinct from Earth. Saturn's realm, Titan and beyond. If Jupiter is the king of the solar system, Saturn is the jewel, crowned by rings that span hundreds of thousands of kilometers, yet are less than 1 kilometer thick in most places. But beautiful as the rings are, they are not habitable. The true prize in the Saturn system is Titan. Titan is Saturn's largest moon and the second largest in the solar system, slightly smaller than Jupiter's Ganymede. It is the only moon with a thick atmosphere, denser than Earth's, composed primarily of nitrogen with methane as a significant component. Titan is also the only place in the solar system besides Earth with stable liquids on its surface, though these liquids are not water, but liquid methane and ethane. Lakes and seas of liquid hydrocarbons fill basins, mostly near the poles. Rivers of methane cut channels through icy plains. Clouds of methane drift through the hazy atmosphere, occasionally producing rain. In many ways, Titan's climate resembles Earth's, but at a temperature of minus 179 degrees Celsius, and with methane playing the role that water plays on Earth. The first human missions to Titan might arrive in the 2060s or later after long voyages from the inner solar system. The spacecraft would use nuclear electric propulsion to reach Saturn, a journey taking several years. Once in orbit, landers would descend through Titan's atmosphere. Landing on Titan would be relatively easy compared to most worlds. The thick atmosphere allows parachutes and aerodynamic braking to slow the descent. The low gravity, about 14% of Earth's, means gentle touchdown speeds. The first landers might settle near Kraken Mare, the largest sea on Titan, a body of liquid methane larger than the Caspian Sea on Earth. The colonists would discover that Titan's environment, while bizarre, offers several advantages. The thick atmosphere provides excellent radiation shielding, better than anywhere else in the outer solar system, except the subsurface oceans of icy moons. While pressure suits are necessary for ventures outside, they don't need to be heavily pressurized since the external atmospheric pressure is actually higher than Earth's at sea level. The atmosphere is not breathable, being mostly nitrogen with no oxygen and significant methane, which is toxic. But the similar pressure means that suit punctures would not be catastrophically explosive as they would be on Mars or the Moon. A breach would allow gases to mix relatively slowly, giving time to seal the leak. Temperature management would be the main challenge. Everything is extremely cold. Water ice at Titan's surface temperature is as hard as rock. The colonists' habitats would need to be heavily insulated and heated by nuclear reactors, which would also provide electricity since solar panels are almost useless this far from the sun. But Titan has resources in abundance. Methane and ethane are essentially unlimited, pooled in vast lakes and seas. These hydrocarbons can be burned with oxygen brought from Earth or manufactured locally to produce energy and water. They can also be processed into plastics, fuels, and chemical feedstocks for manufacturing. Water ice is abundant in the bedrock and can be mined for oxygen and hydrogen. Nitrogen, which makes up most of Titan's atmosphere, is valuable for fertilizer and pressurizing habitats. Titan may even have liquid water beneath its surface, a subsurface ocean like Europa and Ganymede, though this remains unconfirmed. The colonists would establish settlements along the shores of the methane seas. These bases would resemble Arctic research stations on Earth, with pressurized buildings connected by enclosed walkways or tunnels. Greenhouses would produce food under artificial lighting, with air and water carefully recycled. Transportation on Titan would be unique. The low gravity and thick atmosphere make flight extraordinarily easy. Small aircraft and even human-powered flight are practical. A person wearing wings and pedaling a simple propeller could fly through Titan's skies, something impossible on Earth. Boats would sail on Titan's methane seas, exploring the largest bodies of liquid in the outer solar system after Earth's oceans and Europa's subsurface sea. Submarines would dive beneath the surface, investigating the chemistry of liquid methane at nearly 200 degrees below zero. Scientific research on Titan would be immensely valuable. The moon provides a natural laboratory for studying organic chemistry. Titan's atmosphere produces complex organic molecules through reactions driven by sunlight and cosmic rays. These molecules rain down onto the surface, accumulating over billions of years. Some scientists believe the chemistry occurring on Titan resembles what happened on early Earth before life emerged. The possibility of life on Titan is debated. Could organisms exist in liquid methane instead of liquid water, using different biochemistry than Earth life? Some astrobiologists argue it's possible, though no evidence has been found yet. The search continues. Economically, Titan might become important for supplying hydrocarbons throughout the outer solar system. Methane makes excellent rocket fuel when burned with oxygen. It's also useful for manufacturing plastics and other materials. Tankers could carry liquid methane from Titan to settlements on other moons and planets. Saturn's other moons would also attract attention. Enceladus, a small, icy moon only 500 kilometers in diameter, ejects enormous plumes of water vapor from cracks near its south pole. These plumes indicate a subsurface ocean, possibly another location where life could exist. Robotic probes and eventually small research bases might be established to study Enceladus's geysers. The view from Titan would be haunting and beautiful. Saturn would hang in the sky, its rings visible edge-on as a thin line bisecting the planet. When the rings are tilted toward Titan, they become spectacular arcs stretching across the sky. Other moons would be visible as bright points of light. The sun would be a pale disk, only about 1% as bright as seen from Earth. Living on Titan would require adaptation to an alien world. The thick haze that blankets the moon makes the surface dim even at noon. Artificial lighting would be necessary indoors and outdoors. The constant cold means outdoor work must be planned carefully. But the colonists might thrive, building communities and raising families in a world unlike any other. The outer reaches, Uranus, Neptune, and beyond. Beyond Saturn, the solar system grows even more remote. Uranus orbits nearly 3 billion kilometers from the Sun, taking 84 Earth years to complete one orbit. Neptune, even more distant, lies 4.5 billion kilometers from the Sun and takes 164 years to orbit once. These ice giant planets are so far from the Sun that they receive almost no warmth. Surface temperatures on their moons hover around -200 degrees Celsius. The journey from Earth would take years, even with advanced propulsion. Yet these distant worlds possess their own moons worth exploring. Uranus has 27 known moons, though most are small. The 5 major moons, Titania, Oberon, Umbriel, Ariel, and Miranda, are all composed of ice and rock. Miranda is particularly interesting, with a surface featuring extreme geological variety, including cliffs 20 kilometers high, the tallest known cliffs in the solar system. Neptune's largest moon, Triton, is even more intriguing. Triton is slightly larger than Pluto and is believed to be a captured dwarf planet from the Kuiper Belt. It has a thin atmosphere of nitrogen and methane, and its surface features active cryovolcanoes that erupt with nitrogen gas and ice crystals. Triton's retrograde orbit, meaning it orbits opposite to Neptune's rotation, confirms it was captured by Neptune's gravity rather than forming alongside the planet. Colonizing these distant moons would present enormous challenges. The journey alone would take 8 to 12 years with current propulsion technology. Communication delays would be 3 to 4 hours one way, making real-time control from Earth impossible. Sunlight would be so weak that solar panels are nearly useless. Nuclear power would be essential. Yet by the late 21st century or beyond, small research outposts might exist on Triton and Titania. These bases would be primarily scientific, hosting a few dozen researchers who study the outer solar system's unique environments. They would also serve as waypoints for missions to the Kuiper Belt and beyond. Habitats between worlds. While humanity might colonize planets and moons, another form of settlement could emerge: massive space habitats that orbit the sun independently, artificial worlds that travel between planets or remain in stable orbits. These habitats would be based on designs proposed in the 1970s by physicist Gerard O'Neill. The most ambitious are O'Neill cylinders, massive rotating structures that would generate artificial gravity through centripetal force. An O'Neill cylinder would consist of 2 counter-rotating cylinders, each 8 kilometers in diameter and 32 kilometers long. The cylinders would spin to create one Earth gravity on their inner surfaces. Large mirrors would reflect sunlight through windows that run the length of each cylinder, providing natural lighting. The interior surface would be divided into alternating strips. 3 would be land areas where people live and work, and 3 would be transparent windows to admit light. The interior of an O'Neill cylinder would be breathtaking. Standing on the inside, you would look up and see the opposite side of the cylinder curving overhead, kilometers away. Towns, forests, lakes, and farms would spread across the landscape. In the distance, another strip of land arcs upward, eventually meeting at a point far above. Walking toward the axis of the cylinder, gravity would decrease. At the center, there would be zero gravity, perfect for recreation and certain types of manufacturing. People could fly using wingsuits or simply float. Each cylinder could house several million people, more than many cities on Earth. They would be self-contained ecosystems with closed-loop life support systems that recycle everything. Agriculture would be distributed throughout the habitat, with forests providing not only food, but also recreation and psychological benefits. Construction of O'Neill cylinders might begin in the 2070s or later, using materials mined from asteroids. The cylinders would be built in space, never intended to land on planets. They could orbit at Lagrange points, gravitationally stable locations where the Sun and Earth or other planets balance each other's pull. Life aboard would be remarkably Earth-like. Residents would live in houses with yards, work in offices and factories, attend schools and universities. They would enjoy theaters, restaurants, sports facilities. The main difference would be the visible curvature of the world and the ability to see other parts of the habitat overhead. Some cylinders might specialize in different environments. One could recreate tropical rainforests, another temperate forests, another Mediterranean climates. Residents could choose which habitat matches their preferences. Immigration between habitats would be common, with shuttles transporting people and goods. These habitats could become the most Earth-like environments away from Earth. Gravity would be comfortable. Air and water would be abundant. Radiation shielding would be excellent. For people who find planetary surfaces too uncomfortable or dangerous, the cylinders might offer an ideal middle ground. The technologies that make it possible. All of this potential expansion across the solar system would rely on technologies that are gradually maturing. Nuclear propulsion is transforming from theoretical concept to practical reality. Nuclear thermal rockets, first tested in the Nerva program of the 1960s, might finally enter service in the coming decades. These rockets would heat hydrogen propellant with nuclear reactors, achieving twice the efficiency of chemical rockets. Even more advanced would be nuclear electric systems that generate electricity from nuclear reactors and use it to power ion drives or plasma thrusters. These engines produce tiny thrust, but can run for years, gradually accelerating spacecraft to high velocities. They would make missions to the outer planets practical with reasonable travel times. Fusion propulsion remains elusive, but experimental fusion drives are being researched that could demonstrate positive energy gain. These engines might eventually enable much faster travel, reaching Mars in weeks instead of months, and the outer planets in months instead of years. In situ, resource utilization would become ubiquitous. Every settlement would manufacture as much as possible from local materials. Three-dimensional printing with metal, plastic, and regolith would allow on-demand manufacturing of tools, parts, and structures. Closed-loop life support systems would recycle air and water with very high efficiency. Artificial intelligence and robotics would handle tasks too dangerous or tedious for humans. Autonomous mining equipment would work around the clock in asteroid belts and planetary surfaces. Robots would maintain infrastructure, repair equipment, and assist with construction. AI systems would optimize resource allocation, plan logistics, and provide early warning of technical problems. Medical technology would need to advance to handle the unique challenges of space. Drugs to counteract bone and muscle loss in low gravity, genetic therapies to repair radiation damage, artificial organs to replace those damaged by years of exposure to cosmic rays. Telemedicine would allow doctors on Earth to consult with patients millions of kilometers away, though the long communication delays would require substantial autonomy for local medical staff. A solar system transformed. By the end of the 21st century or beyond, according to these speculative projections, the solar system could be utterly transformed. Earth would remain home to most of humanity, but potentially millions might live and work throughout the solar system. Thousands might inhabit the lunar surface. Hundreds of thousands could call Mars home. Tens of thousands might work in asteroid mining operations. Several 100,000 could live in O'Neill cylinders orbiting at various locations. Smaller populations might occupy bases on the moons of Jupiter, Saturn, and beyond. These off-world populations would be young and growing rapidly. Children born on Mars would never have breathed Earth air and might never visit their ancestral home due to the difficulty of adapting to Earth's gravity after growing up in Mars's lighter pull. New cultures could emerge, distinct from Earth, yet connected by constant communication and commerce. The economy of the solar system might dwarf that of Earth alone. Resources would flow between worlds: water from Ceres, metals from metallic asteroids, hydrocarbons from Titan, helium-3 from Jupiter, manufactured goods from orbital factories. Earth would receive wealth in the form of rare materials and technological innovations, while exporting culture, information, and specialized products. Not everything would be peaceful. Disputes might arise over mineral rights, conflicting territorial claims, and political autonomy. Some colonies might declare independence from Earth governments, sparking tensions, but hopefully no wars. The distances involved make military conflict impractical. A war between Earth and Mars would take months to wage, with months between messages and years for reinforcements to arrive. Instead, a solar system-wide economic and political order would gradually emerge, with representatives from each major settlement meeting virtually to discuss common concerns. No central government would rule the solar system, but networks of treaties and agreements would maintain order and facilitate trade. The potential colonization of the solar system could change humanity profoundly. A species that began on one small world might span dozens. We would no longer be bound to Earth's fate. If catastrophe strikes one world, humanity endures on others. Our perspective would shift from planetary to cosmic. We might begin to see ourselves not as citizens of nations, but as members of a species spreading across the stars. Looking up at the night sky from Earth, people might see not just distant lights, but homes where their relatives live, places they might visit, opportunities for new lives. The solar system could become not a void to fear, but a neighborhood to explore. And this might be only the beginning. For beyond the planets, beyond even the Kuiper Belt, where Pluto and countless other dwarf planets orbit, lies the Oort cloud, a sphere of icy bodies surrounding the solar system at distances where the sun is merely the brightest star. And beyond that, the nearest stars beckon, 40 trillion kilometers away, but perhaps not unreachable forever. The potential colonization of the solar system would not be an ending, but a beginning. Each generation might push farther, explore deeper, build more. What could start with a few footprints on the moon might become a civilization spanning worlds. Where once we dreamed of the stars, we might one day live among them. The culture of space, life beyond Earth. As humanity might spread across the solar system, something remarkable could emerge. New cultures, distinct from Earth yet rooted in human nature, might develop in the colonies and stations scattered among the worlds. These would not be merely outposts of Earth civilization transplanted to space, but something potentially novel, shaped by the unique challenges and opportunities of life beyond our home planet. On Mars, a distinct Martian identity might form within the first generation. The colonists would share experiences that no Earth dweller can fully understand. They would have seen their planet from orbit, a small sphere against the black void. They would have worked in spacesuits for hours, feeling the peculiar sensation of lower gravity, the slight delay between movement and response. They would have watched dust storms engulf their world, turning day into twilight, and waited patiently for skies to clear. They might develop their own slang and expressions, words that have specific meanings in the Martian context. A dust-up might be both an argument and a dust storm, the double meaning becoming an inside joke. Going under could mean retreating to the underground habitats during solar storms. Walking soft might refer to the careful gait needed in low gravity to avoid bouncing into ceilings or equipment. Martian colonists would modify their daily routines to match the Martian day, or sol, which is 24 hours and 37 minutes long. This slight difference from Earth days means they would gradually shift out of phase with Earth's schedule. Communication windows with Earth would become increasingly important, times when enough bandwidth is available and latency is minimal enough for meaningful video conversations with family and mission control. Holidays and celebrations might adapt to the Martian environment and calendar. Landing Day, commemorating the arrival of the first human crew, could become the most important Martian holiday, celebrated with extra rations, special meals prepared in the greenhouses, and storytelling sessions where early colonists share their experiences. Earth holidays like Christmas or Diwali or Eid might still be observed by those who wish, but they would take on new meanings in a world without traditional seasons, without familiar landscapes or gathering places. Art would likely flourish in unexpected ways. Painters and sculptors would work with Martian materials, creating pieces from red ochre regolith, polished hematite, and glass made from melted sand. Musicians might compose for the thin atmosphere, where sound behaves differently, muted and lacking high frequencies. Writers would pen poetry and stories about the Martian experience, describing the strange beauty of alien sunsets and the profound isolation of being so far from Earth. Recreation would become essential for psychological health. In a pressurized lava tube habitat, colonists might establish gardens, not for food production, but for beauty. Flowers from Earth seeds would bloom in carefully controlled conditions, their vibrant colors standing in stark contrast to the rust-red landscape outside. Walking paths would wind through planted areas where colonists can stroll without spacesuits, feeling almost as if they're on Earth. Sports would adapt to lower gravity. Basketball could become a three-dimensional game where players can leap several meters high. Running tracks in the lava tube would allow athletes to build speed impossible on Earth, though they must be careful not to achieve escape velocity and slam into walls. Swimming in the small lakes would provide exercise and relaxation, the water's surface behaving oddly in reduced gravity. Children, if they are eventually born on Mars, would grow up with perspectives profoundly different from their parents. They would know Mars as home, not Earth. They would instinctively understand three-dimensional movement in low gravity in ways adults who grew up in Earth gravity never quite master. They would look at images from Earth with wonder, but not longing, seeing alien landscapes of green vegetation and blue water. The question of whether children could develop normally in Martian gravity would weigh heavily on the colonists. Before the first pregnancies are approved, extensive research would be conducted using animals. Mice and rats might reproduce successfully in the low gravity, though their offspring could show some skeletal differences. More research would be needed, but eventually, the decision might be made. Children could be born on Mars. The first Martian baby might arrive in the early 2040s or later, delivered by the colony's medical team in a habitat far from Earth. The birth would be carefully monitored, every vital sign recorded and transmitted back to Earth. The infant would hopefully appear healthy, crying lustily in the thin atmosphere, adapting to the conditions that will be normal for her entire life. As she grows, doctors would track her development carefully. Her bones might be less dense than Earth children's, adapted to lower gravity. Her heart and muscles could be proportionally smaller. She might reach developmental milestones on a slightly different schedule. But she could thrive, learning to walk with an almost floating gait, speaking both English and fragments of the informal Martian dialect that's emerging. When she is 10 years old, discussion might begin about whether she could ever visit Earth. The transition to Earth's gravity might be impossible for someone who grew up in Mars's 3/8 gravity. Her bones might not support her weight. Her heart might not pump blood effectively against stronger gravity. She might be trapped on Mars for life, unable ever to visit the ancestral home of her species. This reality could create a psychological divide. Earth-born colonists retain the option to return home, however difficult the journey. Mars-born children may never have that choice. They could be, in a fundamental sense, a new branch of humanity, physiologically adapted to a different world. Education on Mars would blend traditional subjects with skills specific to the Martian environment. Children would learn mathematics, reading, science, and history through interactive lessons transmitted from Earth and taught by colony members with teaching experience. But they would also learn spacewalking techniques, habitat maintenance, basic geology and chemistry, emergency procedures for equipment failures or medical situations. The educational philosophy would emphasize self-reliance and practical skills. Children would be taught to repair their own equipment, to problem-solve creatively when standard solutions aren't available, to work cooperatively in teams because individual survival depends on the group's cohesion. They would learn Martian history, the stories of the early missions, the names of those who didn't survive the dangerous early years. Similar cultural developments could occur throughout the solar system. On the Moon, a distinct lunar culture might emerge among the permanent residents who work in mining, operations, or scientific research. They might pride themselves on their ability to work in conditions that would kill most humans within minutes, their competence with vacuum-tight seals and life support systems. Lunar colonists might develop efficient communication styles, short and precise, minimizing radio bandwidth and reducing the chance for misunderstandings. Their architecture, both functional and aesthetic, would create spaces that feel human and comfortable despite being carved from dead rock or assembled from metal and polymer modules. Among the asteroid miners, perhaps the most distinctive culture would develop. These would be people who spend years in microgravity, moving between rocks in the belt, living in cramped ships or hollowed-out asteroids. They would develop remarkable three-dimensional spatial awareness, instinctively knowing which way is up even when no direction is preferred in free fall. The miners would be independent by necessity and temperament. When you're 6 months travel time from the nearest help, self-reliance isn't optional. Equipment failures must be repaired with whatever materials are on hand. Medical emergencies must be treated by crews with minimal training. Disputes must be resolved without outside intervention, because there is no outside. This might breed a frontier mentality reminiscent of earlier human migrations. The asteroid belt is vast and largely unclaimed. Ambitious miners would stake claims on promising rocks, filing legal documents with Earth-based registries, but knowing that ultimately, ownership comes down to who actually works a claim. Conflicts might occasionally erupt over disputed claims, usually resolved through negotiation, but sometimes through intimidation or even violence. Law enforcement in the belt would be minimal. Earth governments have limited jurisdiction and less ability to project power across millions of kilometers. The miners might develop their own informal codes, community standards enforced through reputation and mutual agreement. Break the unwritten rules, and you'll find no one willing to trade with you, no one willing to help when your air recycler fails. Stories would circulate through the mining communities, transmitted via radio, and elaborated with each retelling. Tales of massive strikes, asteroids so rich in platinum that a single claim makes someone wealthy for life. Ghost ships found drifting, their crews dead from mysterious causes, their valuable cargo free for the taking for those brave enough to investigate. Prospectors lost in the belt, their beacons failing, their last transmissions philosophical reflections on the beauty and terror of space. the miners might develop superstitions. Certain asteroids could be considered unlucky after several ships experience equipment failures near them. Rituals might emerge for naming newly claimed asteroids, for mourning those lost, for celebrating major milestones like the 100th day of a mission or the anniversary of first leaving Earth. Romance and relationships in space would present unique challenges and opportunities. Crews thrown together for months or years would inevitably form bonds, sometimes romantic or sexual. The early missions might explicitly prohibit intimate relationships, worried about complications and conflicts. But as missions lengthen and colonies become permanent, such restrictions would become impossible to maintain. Couples would form among the colonists. Marriages would occur. Celebrations adapted to available resources and conditions. Wedding ceremonies on Mars or in orbit around Jupiter would carry their own unique character. Vows exchanged while floating in microgravity or standing on alien soil beneath unfamiliar skies. Some relationships would flourish in the forced closeness and shared purpose of colony life. Others would collapse under the stress and isolation. Divorces would happen, complicated by the fact that separating physically might be impossible when both partners live in the same small habitat and the next launch window back to Earth is months or years away. The psychological challenges of space living cannot be overstated. Isolation, confinement, danger, distance from friends and family, the alien nature of the environment, all contribute to mental health issues. Depression would be common. Anxiety disorders would emerge. Occasionally, more severe problems like psychosis might manifest. Colony medical staff would include psychologists and counselors, but they too would be isolated, dealing with their own adjustment issues. Medication would help some people. Therapy sessions conducted via video link with specialists on Earth would suffer from communication delays, but provide some support. But ultimately, colonists would need to develop their own coping mechanisms, finding meaning and purpose in their daily work and in their relationships with crewmates. Technology would continue advancing, gradually improving conditions throughout the solar system. Life support systems would become more reliable, requiring less maintenance and achieving higher recycling efficiency. Habitat designs would evolve based on experience, incorporating better radiation shielding, more efficient layouts, improved air and water quality. Communication systems would improve bandwidth and reduce latency through relay satellites and better signal processing. While the speed of light still limits how quickly messages travel, colonists might eventually stream video from Earth with only seconds or minutes delay rather than hours. This would help maintain cultural connections and reduce the sense of isolation. Medical technology would adapt to space conditions. Telemedicine systems would allow Earth-based specialists to guide local practitioners through complex procedures. Surgical robots could be operated remotely, though latency makes real-time control impossible for distant colonies. Pharmaceutical manufacturing in space would produce medications locally rather than waiting for resupply from Earth. Food production would improve dramatically. Early missions would survive on packaged food supplemented by small greenhouse crops. Later colonies would develop extensive agricultural capabilities, producing not just calories, but variety and quality. Chefs in the colonies would create new cuisines combining Earth traditions with locally grown ingredients and the constraints of space living. Genetic engineering might contribute to food security. Crops could be modified to thrive in low gravity, artificial light, and hydroponic systems. Animals like chickens and fish might be adapted to produce more efficiently in space conditions. Eventually, lab-grown meat could become practical, creating protein without the need to raise and slaughter animals in resource-limited environments. Energy production would evolve beyond early solar and nuclear systems. Fusion power might remain frustratingly close but out of reach throughout the mid-21st century. Experimental reactors might achieve energy break-even, producing as much energy as they consume. But commercial fusion plants that produce more energy than they use might remain elusive for decades. Instead, colonies would rely on improved versions of existing technologies. Solar panels would become more efficient, capturing larger percentages of available light. Nuclear fission reactors would grow safer and more compact, providing reliable baseload power. Advanced batteries would store energy more efficiently, helping manage supply and demand. Transportation within the solar system would gradually become cheaper and more routine. Reusable spacecraft, pioneered by SpaceX's Starship but potentially adopted by many companies, could drive down launch costs. Nuclear electric propulsion systems might enable faster travel to distant destinations. Water extracted from asteroids and the outer moons could provide propellant at strategic depots throughout the system. A network of orbital stations might develop, waypoints where spacecraft refuel and crews rest between legs of long journeys. These stations could orbit at Lagrange points, gravitationally stable locations where the gravity of the Sun and planets balance. Stations might exist at Earth-Moon L1, Earth-Sun L1 and L2, Mars-Sun L1, and eventually at Lagrange points throughout the system. The stations would serve multiple purposes beyond fueling and crew transfers. They might be research facilities studying physics and astronomy in unique locations, manufacturing centers producing goods impossible to make in gravity wells or atmospheres, hotels and recreational facilities for space tourists and workers on leave, repair yards where damaged spacecraft undergo maintenance. Trade routes could emerge between the various settlements. Water would flow from the asteroid belt and outer moons to the inner system. Metals would move from mining operations to orbital factories. Manufactured goods, pharmaceuticals, and advanced electronics would ship from Mars and lunar industries to frontier settlements. Food concentrates would travel from agricultural stations to mining operations in the belt. An economic system might develop that's neither purely capitalist nor socialist, but a hybrid adapted to space conditions. Private companies would operate mines and transport services. Governments would fund research and maintain critical infrastructure. Cooperatives might manage some agricultural and manufacturing operations. Individual prospectors would work claims in the belt. All would exist in a complex web of competition, cooperation, regulation, and mutual dependence. Currency would pose interesting challenges. Earth-based money would work for transactions with Earth, but colonies might develop their own internal economies using local currencies or even barter systems. Oxygen and water could become de facto currencies in some locations, measured in cubic meters or kilograms, and traded for other goods and services. Digital currencies designed for high-latency networks might enable transactions across the solar system despite communication delays. Governance structures would likely vary widely between settlements. Some might operate as democratic communes where all residents participate in decision-making. Others could function as company towns controlled by the corporations that established them. Still others would be military or scientific outposts answering to government agencies on Earth. Conflicts would inevitably arise over resources, territories, and political autonomy. Mars might declare itself independent from Earth nations in the 2050s or later, establishing its own planetary government while maintaining trade and communication ties. The process would likely be tense, but hopefully peaceful. Earth governments reluctantly accepting that they have limited ability to enforce their will across interplanetary distances. Smaller conflicts would occur regularly. Disputes over mining claims in the asteroid belt might sometimes escalate to violence. Stations in orbit would compete for advantageous positions. Colonies would argue about water rights and trade terms. Most conflicts would likely be resolved through negotiation or arbitration, but the potential for more serious confrontations would always exist. The question of military force in space would remain contentious. Earth nations might maintain some military spacecraft, ostensibly for defending satellites and space infrastructure. But weapons in space would likely be limited by treaty, and the vast distances make military operations impractical. A war between Earth and Mars would take months to wage, with months between messages and years for reinforcements to arrive. Instead, soft power and economic interdependence might maintain order. No colony could survive without trade with others. Earth would supply advanced manufacturing equipment and expertise. Mars would provide metals and water. The asteroid belt would export raw materials. The outer system would send hydrogen and helium. Break the peace, and you cut yourself off from resources you need for survival. Religion would likely adapt to space living in interesting ways. Some colonists might find their faith strengthened by the profound experience of seeing creation from a new perspective. Others might lose faith, finding it difficult to maintain traditional beliefs when confronting the vastness and apparent emptiness of the universe. New religious movements might emerge, some drawing on traditional faiths but adapting them to space contexts, others creating entirely new belief systems. Some colonists might worship the cosmos itself, seeing divinity in the stars and planets. Others might develop philosophies emphasizing humanity's duty to spread life through the universe, a kind of secular religion of expansion and growth. Services and rituals would occur in whatever spaces are available. Mosques, churches, temples, and meditation rooms might be established in habitats when possible. When dedicated spaces aren't available, common areas would serve multiple purposes. Prayer times would work around work schedules. Holidays would be observed even when they fall at inconvenient times by colony calendar. The concept of environmental stewardship would take on new meaning in space. On Earth, environmentalism often focuses on preservation, protecting natural areas from human impact. In space, the goal would be creating and maintaining livable environments where none existed. Every breath of air, every drop of water, every scrap of biomass would be precious because it sustains human life in a hostile void. This might create an almost religious devotion to recycling and waste reduction among colonists. Nothing would be thoughtlessly discarded. Organic waste would be composted. Metals would be melted down and reused. Water would be purified and recycled hundreds of times. The concept of a closed-loop economy where all materials cycle endlessly would become not just a theoretical ideal, but a practical necessity. As the decades pass and humanity spreads farther through the solar system, the question would arise: are we still one species, or are we fragmenting into multiple? The physical differences between Mars-born and Earth-born humans would be small but present. Would they accumulate over generations? Would colonies in the outer system, where gravity is even lower and radiation even stronger, develop even more distinct characteristics? Some scientists might predict that within a few centuries, humans on different worlds could become reproductively isolated, unable to interbreed with each other due to accumulated genetic differences. Others might argue that genetic engineering and continued migration will prevent such fragmentation, maintaining human unity even across the vastness of space. Philosophically, the question of human identity would become central to space culture. What does it mean to be human when humans live on a dozen worlds under vastly different conditions? Is humanity defined by biology, by culture, by shared history? These questions don't have easy answers, but colonists would grapple with them constantly. The economics of infinity money and wealth might flow through the solar system in ways that could transform both space colonies and Earth itself. The early decades of space expansion would be funded primarily by governments, expensive projects justified by scientific discovery, national prestige, and long-term strategic goals. But as resource extraction industries mature, private capital might flood into space ventures. Asteroid mining could prove particularly lucrative once the initial infrastructure is established. A single metallic asteroid, a few hundred meters across, might contain more platinum than humanity has mined in all of recorded history. The first companies to successfully extract and return these resources to Earth, orbit or Earth's surface, could become spectacularly wealthy. Their founders and early investors reaping returns that dwarf previous industrial fortunes. But the real economic transformation might come not from exporting resources to Earth, but from using them in space. The cost of lifting material from Earth's surface to orbit is enormous, thousands of dollars per kilogram, even with reusable rockets. Material extracted from asteroids or lunar mining operations would already be in space, requiring no expensive launch. This makes it far more practical for construction projects in orbit or on other worlds. Manufacturing industries might relocate to space to take advantage of this cheap material and the unique conditions available. Microgravity allows creation of materials and structures impossible in Earth's gravity. The high vacuum of space enables processes that require expensive vacuum chambers on Earth. The extreme cold of permanently shadowed craters allows superconducting materials to operate without refrigeration. Orbital factories might produce everything from spacecraft components to advanced electronics to pharmaceuticals. Some products would be sold back to Earth, but increasingly, the space economy could become self-sustaining, producing for space markets rather than terrestrial ones. Habitats need structural materials, electronics, life support equipment. Spacecraft need engines, power systems, hulls. Colonies need agricultural equipment, medical supplies, tools. Service industries might emerge to support the growing population living and working in space. Transportation companies would operate cargo haulers and passenger ships. Communication firms would maintain relay networks. Banks and financial services companies would manage the flow of money between worlds. Insurance companies would assess risk and provide coverage for everything from spacecraft to lives. Entertainment and media companies might produce content specifically for space audiences. Virtual reality systems could allow colonists to experience simulated Earth environments, walking through forests or swimming in oceans they may never see in person. News organizations with correspondents throughout the system would provide coverage of events on multiple worlds. Educational companies would deliver training and courses to isolated outposts. The accumulation of wealth in space could create new social divisions. Some colonists might become rich from successful mining claims or business ventures. Others would remain working class, employees of companies or government agencies, doing difficult, dangerous work for modest pay. The promise of equality and shared hardship in the early colonies might give way to economic stratification as prosperity grows. Labor organizing might begin among miners and industrial workers. Strikes could occur, complicated by the fact that withdrawing labor in space can be life-threatening if critical systems aren't maintained. But workers might develop sophisticated tactics, work slowdowns and sick-outs that press demands without crossing into truly dangerous territory. Universal basic income schemes might be implemented in some colonies. everyone receiving enough resources for survival while being free to work for additional compensation. Other settlements might maintain more traditional capitalist structures. Still others could experiment with different economic models, testing theories about allocation and incentives in small, isolated populations where results are easy to measure. The tension between space as frontier paradise and space as new arena for old human conflicts might never quite resolve. Some colonists would flee Earth to escape economic inequality or political oppression, seeking fresh starts on new worlds. But human nature would accompany them, and familiar patterns might eventually reassert themselves. Tourism could become a significant industry as space access becomes more affordable and routine. Wealthy individuals might pay for trips to orbit, to lunar bases, even to Mars. Hotels and recreational facilities would cater to these visitors, providing experiences unavailable on Earth. Spacewalking excursions, lunar rover races, Martian hiking expeditions, all could become popular tourist activities. The tourism infrastructure would require significant investment, but could generate substantial revenue. Spacecraft designed for passenger comfort rather than cargo efficiency. Trained guides and safety personnel, insurance and medical support, marketing and booking systems. Eventually, tourism revenue might rival industrial and scientific activities in some locations. The cultural exchange between tourists and permanent residents could be complex. Tourists would bring news, perspectives, and money from Earth. They would be fascinated by the colonies, eager to understand how people live so differently. But to permanent residents, they might sometimes be resented as dilettantes playing at space life without facing its real challenges and dangers. Wealthy individuals might establish private estates on Mars or the Moon, claiming large territories and building luxurious compounds. Some would be criticized as vanity projects, resources wasted on mansions rather than expanding habitats for more colonists. Others would employ local workers and contribute to the economy, their conspicuous consumption creating jobs and demand for goods and services. The distribution of land and resources on other worlds would raise thorny legal and ethical questions. Earth-based property law doesn't translate well to space. The Outer Space Treaty declares that no nation can claim sovereignty over celestial bodies, but it's unclear how this applies to private claims or settlements. Who owns the Moon, Mars, individual asteroids? Various legal frameworks might be proposed and partially implemented. Some would argue for homesteading rules where occupying and developing territory grants ownership. Others would advocate for common heritage principles, resources owned collectively by humanity and developed for mutual benefit. Still others would push for auction systems, where governments or international bodies sell rights to private entities. In practice, a patchwork of informal arrangements might emerge. Mining companies would claim asteroids, and their claims would generally be respected by others if actively worked. Colonies would claim territories around their settlements, expanding as population grows. Disputes would arise and be settled through negotiation, arbitration, or occasionally force. The question of taxation across space would become complicated. Earth governments might initially claim authority to tax their citizens working off-world, but enforcing compliance would be difficult when people are millions of kilometers away. Some colonists might simply stop paying, declaring themselves independent. Others would negotiate new arrangements, paying reduced taxes in exchange for specific services like emergency support or trade facilitation. Space settlements would establish their own tax systems, raising revenue for public services and infrastructure. Some might tax income, others tax property or resource extraction. Many would rely on fees for services rather than broad taxation. The economic experiments conducted across the solar system would provide valuable data about what taxation schemes work well under different conditions. Trade agreements between Earth and space colonies and between different space settlements would establish frameworks for commerce. Tariffs would be debated, some arguing for free trade to maximize efficiency, others wanting protection for local industries. Standards would be negotiated for safety, quality, and compatibility. Currency exchange rates would be established, complicated by latency issues when transactions take hours to confirm. The solar system economy could become a web of interdependence. Earth would supply advanced technology, expertise, and cultural products. Mars would export metals, water, and increasingly, manufactured goods. The Moon would provide raw materials and serve as a logistics hub. The asteroid belt would supply resources at advantageous locations throughout the system. The outer moons would export ice and volatiles. This interdependence might help maintain peace despite tensions and conflicts. Breaking economic ties would hurt everyone. Colonies that attempt autarky, trying to be completely self-sufficient, would struggle to match the efficiency and variety achievable through trade. Specialization and comparative advantage would work in space as on Earth. Different locations focusing on what they do best and trading for everything else. Financial markets might develop specifically for space commerce. Commodity exchanges would trade futures contracts for water, oxygen, metals, and other resources. Stock markets would allow investment in space companies. Venture capital funds would finance new colonial ventures and technological developments. Banks would provide loans for everything from spacecraft purchases to habitat expansion. Risk management would become a sophisticated industry. The dangers of space travel and habitation require extensive insurance coverage. Actuaries would calculate premiums based on mission profiles, destination risk, crew experience, and countless other factors. Some risks would be deemed uninsurable, too uncertain, or too likely to result in total loss. The flow of wealth back to Earth might transform terrestrial economies as well. Mining companies and their investors would reap enormous profits, creating new fortunes. Space industries would employ millions of people on Earth in design, manufacturing, and support roles. Demand for space-related products and services would stimulate innovation and economic growth. But the benefits would likely be unevenly distributed, as always. Wealthy nations and individuals would gain more from space development than poor ones. Countries without space programs would fall further behind technologically and economically. Within nations, the space industry would enrich some regions and demographic groups while bypassing others. Social movements might emerge calling for space resources to benefit all humanity, not just the wealthy and privileged. International agreements could establish funds where a portion of space revenues support development on Earth, providing clean water, education, healthcare in regions left behind by technological progress. But enforcement might remain weak, and actual resource transfers modest compared to the scale of space wealth. The old question of whether space expansion helps or hurts Earth might never find a definitive answer. Optimists would argue that resources from space reduce pressure on Earth's environment, that technologies developed for space benefit everyone, that inspiration from exploration motivates people and drives progress. Pessimists would counter that money spent on space could address immediate human needs on Earth, that space benefits primarily accrue to elites, that expansion perpetuates patterns of exploitation and inequality. Both perspectives would contain truth. Space development would produce benefits that flow back to Earth. Technologies created for space would find terrestrial applications. Resources from asteroids would supplement Earth's dwindling reserves of certain metals. The sheer ambition of the project would inspire people and drive scientific advancement. But the benefits would be real yet limited, and they wouldn't address root causes of poverty and environmental degradation on Earth. Ultimately, space expansion might proceed not because it solves Earth's problems, but because humans are driven to explore and settle new frontiers. The economic justifications and scientific rationales would be real, but secondary to the fundamental human impulse to see what lies beyond the next horizon, to build new homes in new places, to spread across the cosmos simply because we can. And so the settlement might continue, the economy grow, and humans spread farther and farther from the world that birthed them, potentially building new civilizations among the stars. The colonists who leave Earth seeking adventure or opportunity, the scientists pursuing questions that can only be answered among the stars, the families who build homes and raise children under alien skies. Life in space and on distant worlds would be difficult. The dangers would be real and constant. Equipment would fail. Accidents would happen. People would die. But those who choose this life would accept the risks because the rewards, psychological if not always material, could be profound. There might be the scientist on Europa who first peers through a camera into the alien ocean and sees bioluminescent life glowing in the darkness. The child born in Olympus Mons, base on Mars, who climbs to the crater rim and looks out across a landscape that's home in a way Earth never could be. The engineer on Callisto who solves a critical problem and saves her crewmates from disaster. The poet who writes verses in low gravity describing the view of Saturn's rings from Titan's surface. These moments, multiplied by millions, could create something new. A multi-planetary civilization where humanity is no longer defined by the world that birthed it, but by the curiosity, courage, and creativity that drive us to explore. On clear nights, colonists throughout the solar system might pause in their work and look up. From Mars, they would see Earth as a bright blue star. From Titan, they would see Saturn's glorious rings. From lunar bases, they would watch Earth rise over the horizon. And they would remember that they're all part of something larger, a species that refused to stay confined to one world, that looked up at the stars and decided to go there. The potential conquest of the solar system is ultimately not about economics or politics or even survival. It's about fulfilling the potential that's always existed within us, the potential to explore, to discover, to build, to dream. And as we conclude this journey through a possible human future, consider that somewhere out there in tomorrow, someone might be looking up at stars from the surface of Mars or Titan, or some habitat between the worlds. They might be thinking about their lives, their hopes, their futures, and they might be grateful to the generations before them who made it possible. Perhaps one day, you might be one of those people. Perhaps your descendants will. Or perhaps you'll simply watch from Earth as humanity potentially spreads across the solar system, proud to be part of the species that reached for the stars and made them home. Either way, the future is out there, waiting to be built. One habitat at a time, one settlement at a time, one person at a time. Until one day, we might look back and realize we've done it. We might have conquered the solar system, not through force, but through determination. Not as conquerors, but as explorers and settlers. Not to dominate, but to thrive. And when that day comes, when millions of humans might live and work throughout the solar system, when new generations born on distant worlds look up at Earth and see it not as home, but as history, we'll know we've succeeded. We might have become a truly spacefaring civilization. And if you enjoyed this speculative journey through humanity's potential future among the stars, or if it sparked your curiosity about what's possible when we reach for the cosmos, please consider liking and subscribing to Quiet Science Channel. Your support helps others discover these explorations of science and possibility. Until next time, may your curiosity guide you to new horizons.